Chapter 2 is about linear equations and functions. So the first section, 2.1, is talking about what a relation in a function actually is. So first off, let's start with a relation. A relation is a mapping or a pairing of input values with output values. A function is you put in something, you get out something else. In this case with numbers, we're putting in one number into a function, and in the end we're going to get out a different number. Just like if you put in a quarter in a soda machine and you get a soda out. Or you put bread into a toaster and you get toast out. Or you put food into your mouth and you get, well, we won't talk about what comes out, but you get the idea. A relation is you have a set of input values, you put it into this function, and you get out something different. We're going to talk about the different ways you can represent functions. There are 4 ways you can represent a function. First off is right here, talking about ordered pairs. You can list relations as ordered pairs. Here we have the ordered pairs -2, 2, -2, -2, 0, 1, 3, 1. This is a relation, this set of ordered pairs. You can also represent them using a table. This is the second way. A table, we have our x values in this column, our y values in this column. You can see I just took these ordered pairs and I put them in a table. Same ordered pairs, just represented in a different way. You can also put them on a graph. We can plot these points on a graph. So if I plot this, our first point we have -2, 2, the left 2, up to, here's that point. -2, -2 would be right here, 0, 1, and 3, 1. Now remember that this is our x-axis and this is our y-axis. So -2, 2, I went to the left, -2 on the x and up 2 for the y. So this is representing the same set of ordered pairs in a third way as a graph. So these are all the same ordered pairs, just represented in a different way. The fourth way is in a mapping diagram. And here we have 2 columns. The left one is our input values, and the right one is our output values. Or in this case, x and y. X is your input values and y is your output values. So in a mapping diagram, we list our x values in the input column. And if you have more than one of the same number, you don't have to list it twice. So here we have 2 -2's in the x column. We just list that once. You don't have to list it twice. We also have a 0 and a 3. And in our output column, our y's, we have a 2, a -2, and we have 1 twice. We don't have to list it twice. So the mapping comes in connecting our inputs and outputs. So over on this table, or in the ordered pairs, you can look either way. I know that -2 is mapped or paired with 2. So I'm going to draw a line from -2 to 2. -2 is also paired with -2. So -2 also is paired with -2. My 0 is paired with the 1, and my 3 is also paired with the 1. So that is your mapping diagram, the fourth way to identify your relation. We're going to do an example on representing relations. So here the problem says to consider the relation given by the ordered pairs. So we're considering all these ordered pairs listed. The first thing they want us to do is identify the domain and the range. If you don't remember, the x values are your domain values and the y are your range values. So when it says identify the domain and the range, the domain are all the x values. And when you list them, you should list them in brackets, and it's better to list them in order. So first, the domain. The domain, again, are the x values, so you just list your x values. We have -2, we have a -1, we have a 1, and we have a 2, and we have a 3. That was easy because they were already in numerical order. The range are your y values, so it looks like we have a -3, And we also have a 1, 3, negative 2, and 1. The next in numerical order would be negative 2. And then it looks like we have a 1 twice. You don't have to list that twice, just list it once. And then our last, we have a 3 over there. So this is our domain and our range. Next, we want to represent the relation using a graph and a mapping diagram. So first off, to represent it as a graph, you just plot the points. Nothing too difficult. So we have the point negative 2, negative 3, which is going to go there. And we have negative 1, 1. And 1, 3. Two, negative 2, and 3, 1. 2, negative 2, and 3, 1. So that is the relation represented as a graph. So the mapping diagram is where you would draw your two boxes. This is our x values and our y values, or our inputs and outputs, all the same thing, interchangeable words. Our x values, this is where we list our domain and our range, because remember in our range we had 2 1s. We don't want to list that twice, just list it once. So our domain was negative 2, negative 1, 1, 2, 3, and our y's negative 3, negative 2, 1. There were 2 of them. Don't list them twice, just list it once. So our pairings. Negative 2 was mapped to negative 2. Negative 1 was paired with 1. 1 was paired with 3. 2 was paired with negative 2 as well, and 3 was also paired with 1. So that is your mapping diagram. Up until this point, we've only talked about relations. All sets of numbers are relations, but now we're going to identify what a function is. And a function is a relation in which each input has exactly, very important, one output. So a function, the input has exactly one output. So if I have a couple different mapping diagrams here, let's say this is my x and my y, and I have negative 3, negative 1, 2, 4, 2, 3, negative 4. And let's say my 3 is mapped to 2, my negative 1 is mapped to 3, and both 2 and 4 are mapped to negative 4. To tell whether it's a function is we have to look at every input and see if it has exactly one output. Negative 3 only has an output of 2. 1 also only has one output. 2 only has one output, and 4 only has one output. So this is a function. Just because these two both go to negative 4, that's okay, because 2 is only connected to one thing over here, and 4 is only connected to one thing over here. It's okay that it's connected to the same thing. That's fine. So this is a function because every input only has one output. So another example, if we had negative 2, 1, 4, negative 4, negative 1, 2, and 3, and let's say these two were mapped, and 1 was mapped to both of these, 4 was mapped to 3. Now to see if this is a function, check to see if every input has only one output. These are our inputs, these are our outputs. -2 only has one output, 4 only has one output, but here we see that 1 has two outputs. 1 is mapped to both -1 and 2. So this is not a function, because the input 1 is mapped to both -1 and 2. So a function is every input only has one output. So let's say you were looking at the graph and not the ordered pairs. Like up here it gave us the list of ordered pairs in a map. Let's say it just gave us a graph, and that's what we were looking at. Let's say we were looking at these two parabolas, and they wanted to know, is this a function? Well, there's something called the vertical line test. If you draw a vertical line, imaginary ones, I'm just going to draw some dotted ones, and you took this vertical line and you swept it across the graph from left to right. If this graph only touches at one point, then it's a function. So you see here, if I draw a line, it only touches one point. Here I draw a line. No matter where I draw a vertical line, it's only going to touch once. Then this is a function. And it's the same reason, because every input only has one output. For example, if this was 4, let's just say this was where x equaled 4. Up here, there's only one value for 4. My input, my x, only has one output. If we were looking at something like this, a sideways parabola, if I do the same thing and I draw vertical lines, you see how it touches at 2 different points? Same reason, let's say if this was 4 again, 4 now has 2 y values, a positive one and a negative one. So now it is not a function. The last thing I want to go over is kind of a reminder what linear functions are. A linear function is always in this form, y equals mx plus b, where m is your slope and b is your y-intercept. In these examples, we want to tell whether the function is linear and then evaluate it where x equals -4. So if we look at this first one, f of x equals -x squared minus 2x plus 7, is this linear? Well, no, it's not, because it has an x squared term. And linear does not have x squared, it just has a number times x and then plus or minus a constant. So no, it's not. But then it says we want to evaluate where x equals -4. So then I'm going to evaluate at -4, so I put -4 in for x. And when I do my math, -4 squared is 16, make that negative. That becomes a positive 8 plus 7, which gives me -1. In my second example over here, the g of x tell whether this is a function, or I'm sorry, a linear function. Yes, it is linear because it just has a number times x plus or minus a constant. So yes, this is linear. And evaluate it at -4, so we plug in -4 for x. So g of -4 and when I evaluate that, get -12. Just a reminder that this g of -4 is called functional notation, and it does not mean g times -4, it means g of -4. So instead of x, it means plug in -4 in for x. I want you to go ahead and do this problem in your notes. Find the domain and range here, put them in the brackets, and then tell whether it's a function and why it is or is not a function.